I am Mohua Nandipal, Assistant Professor, CSC Department, MCKV Institute of Engineering. In this video, I am going to discuss the introduction of basic memory management. To understand basic memory management, some preliminary concepts are discussed in this video. Memory allocation is generally performed through two methods, static allocation and dynamic allocation. In static allocation, memory allocation is done before execution. Compiler may produce absolute code or relocatable code. In dynamic allocation, the memory allocation is delayed till the process starts its execution. Regarding logical and physical address. Since in dynamic allocation, the process of allocation of the process is not known at compile and load time, the processor at compile time generates some addresses known as logical address. The set of all logical addresses generated by the compilation of the process is known as logical address space. These logical addresses need to be converted into absolute addresses at the time of execution of the process. The absolute addresses are known as physical addresses. The set of physical addresses generated corresponding to the logical addresses during process execution is known as physical address space. Swapping is another memory management related phenomena. The action of taking out a process from main memory is called swap out, and the action of bringing back the swapped out process into main memory is called swap in. A separate swap space should be existent in the hard disk for swapping in and swapping out. Now we are considering one example of swapping. A process of size 200 MB needs to be swapped into the memory, but there is no space in the memory. A process of size 250 MB is lying idle in the memory and therefore it can be swapped out. How much swap time is required to swap in and swap out the processes if average latency time of the hard disk equal to 10 millisecond, transfer rate of hard disk equal to 60 MB per second. So we need to work out this problem. The process that is required to be swapped in of size 200 MB and the process which is required to be swapped out from the memory that is of size 250 MB. So process size is given over here, that is 200 MB, and transfer rate of hard disk that is also given equal to 60 MB per second. So transfer time for swap in equal to 200 by 60, that is 3.34 second or 3340 millisecond. And average latency time of the hard disk that is also given equal to 10 millisecond. So the total swap in time equal to 3340 plus 10 millisecond equal to 3350 millisecond. Now regarding the total swap out time. Transfer time for swap out 250 is the size of the process divided by 60 equal to 4.17 second equal to 4170 millisecond, and the average latency time equal to 10 millisecond. So total swap out time equal to 4170 plus 10 equal to 4180 millisecond. So total swap in and swap out time, that is total swapping time equal to 3350 plus 4180 equal to 7530 millisecond. One assignment is given regarding swapping. A process of size 300 MB needs to be swapped in from hard disk. But there is no space in the memory. It was found that two processes of size 150 MB and 200 MB are lying idle and can be swapped out. So, the process of size 300 MB will be swapped in, and the processes of sizes 150 MB and 200 MB will be swapped out. How much swap time is required for swap in and swap out the processes if the following is given? Average latency time of the hard disk equal to 10 millisecond and transfer rate of hard disk equal to 60 MB per second. We require to find out the total swap time. Now regarding base or relocation register and limit register. In a multiprogramming environment, the memory is shared among multiple processes. Due to this, it may not be possible to know in advance which processes will reside in the memory and their locations. Therefore, static allocation may be difficult. To implement relocation, some hardware support is required. There should be a processor register which holds the base address. This register is known as base register or relocation register. Base register holds the starting address in the main memory from where the process needs to be relocated. Along with the base register, there should be a register that stores the ending location of the process, that is, the knowledge of the limit of the process in the memory. The limit is stored in a limit or bounds register. The relocation process is explained in this slide. When the process starts executing, relative or logical addresses are generated by CPU. These relative addresses are first added in the base register to produce an absolute address or physical address. Next, the address is compared with the address stored in the limit register. If the address is less than the limit register address, the instruction execution continues. Otherwise, an interrupt will take place. In a multiprogramming environment, there is always an issue of protection of user processes. They should not interfere with other processes and even with the OS. Therefore, it is required that the process should not be able to enter the memory area of other processes or the operating system itself. Each process should execute within its allocated memory. These requirements can be assured with the implementation of base and limit register. So this is the diagram explaining memory mapping using base and limit register. We are considering one example regarding relocation. A process is to be swapped in at location 20100 in memory. If logical addresses generated by the process are 200, 345, 440 and 550, what are the corresponding physical addresses? So we are getting the content of the base or relocation register as 20100 and the logical addresses generated are these. So we have to sum up the content of base register with the logical addresses. So we are getting 20100 plus 200, that is 20300 as the physical address. In the second case, we are getting 20445 as the physical address. And when 440 is generated as logical address, it is added to the base register content 20100 and we are getting physical address 20540. And when the logical address is 550, we are getting 20650 as the physical address. The second example we are considering regarding relocation is a process has relocatable code of size 900K. The relocation register is loaded with 40020K. Means the content of the relocation or base register is 40020K. And the limit register contains the address 41000K. If the processor generates a logical address 990, where will it be located in physical memory? So, in this case, we are getting 40020 as the content of base register and the generated logical address is 990. So we are getting the physical address by adding them up, that is 40020 plus 990, that is 41010 is the physical address generated. But the content of limit register is 41000 and our generated physical address 41010 is greater than the content of the limit register. So the process will not be allocated in this case and the interrupt will be generated. One assignment is given over there where 3 columns are there. The first column indicates the segment numbers, second column indicates the content of the base register and third column indicates the length. And what are the physical addresses? The format of the physical addresses segment, comma, address for the following logical address. For 0th segment, the logical address generated is 430 and the base register content for 0th segment is 219. So the logical address generated 430 will be added to the base register content 219 and we will be getting the logical address. We are getting the physical address. If the obtained physical address exceeds the length, then the interrupt will be generated. In case of second segment, the logical addresses generated is 500 and the base register content is 90. So physical address will be 90 plus 500, that is 590. But the length of the segment is 100. The length of the memory segment is 100. So it exceeds the length of the memory segment. So interrupt will be generated. In this way, all the 5 cases will be solved. In my next video, I'll be discussing fixed and variable memory partitioning. As references of my lecture, I have used Operating System Concepts by Silversage, Galvin and Gagne from Wiley Publication and Operating System Principles by Naresh Chauhan from Oxford University Press. If you have any question, you can put your question in the mail ID mohuha.nondi@gmail.com or you can put the question in the comment section below. Thank you.